Hello everyone, my name is Meng Lian. It is my honor to attend the ISPD virtual conference. Our topic today is FXT router, efficient high-performance PCB routing with crosstalk reduction using spiral delay lines. In the following, I will introduce our routing method, which adopts the spiral delay lines to address the delay matching issue, while effectively reducing crosstalk noise and achieving high-density transmission lines. Adding serpentina delay lines is the common delay matching technique to balance the delays of time-critical signals. Serpentina topology, however, can induce simultaneously accumulation of the crosstalk noise, resulting in speed-up effects. The state-of-the-art approach enlarges the wire separation to alleviate the crosstalk. In the following, we elaborate on the propagation of the main signal and the crosstalk along the serpentina and spiral delay lines. Suppose that at time 0, the main signal appears at the near end of L1. The signal simultaneously induces crosstalk noise in all other segments. As the signal propagates along L1, the crosstalk pulses propagate from L2, L4, L6, and L8 to L3, L5, L7, and L9 respectively. After that, the main signal travels along L2 and induces additional rightward propagating crosstalk. The process of crosstalk accumulation is repeated until the main signal reaches the receiver at time 90D. As shown in the figure, the accumulation of adjacent crosstalk may exceed the threshold of logic switching at the receiving end before the main signal's arrival, leading to a speed-up effect on the wire. As with serpentina delay lines, at time 0, the main signal switches at the near end of L1 and propagates from left to right. Meanwhile, the adjacent crosstalk pulse induced by the main signal proceeds straight to the receiver. After that, the main signal propagates to the far end of L8 and induces two adjacent crosstalk pulses. As shown in the figure, the crosstalk is spread over time ahead of the main signal. Consequently, regardless of the number of line segments, the erroneous logic gate triggering does not occur as long as K1 over 2 is smaller than the voltage threshold at the receiving end. Our method generates one wire at a time, starting from the edge of the routing area and maximally reserving the center for unrouted wires. We implement our routing algorithm by constructing a mixed integer linear programming model to determine the wire's main path between its two target pins alongside the boundary of free routing area. Generally, our algorithm selects bending point candidates to serve as bending points to form the wire's main path. After that, we add spiral delay lines to compensate for the required wire length. As the orientation of the spiral's terminals can be either at opposite corners or on the same edge, we define two primary spiral types, convex and concave spirals. We show the areas for spiral synthesis for convex and concave corners in the figure. Further, we provide a weight coefficient for each boundary's corner to reflect the severity of routing congestion. We implement our method for spiral synthesis by constructing a quadratic programming model. In the following, we investigate the performance of the along-the-edge routing model and our length composition technique using 6 layout designs as test cases. The table demonstrates the routing efficiency of our method. A smaller free space ratio indicates less wasted area. As demonstrated in the table, our method can effectively reduce the free space ratio to less than 18% in all cases. On average, the required routing area decreases by 31% compared to the original result, leading to lower manufacturing costs. Further, we show the experimental results for case 6. Figure A shows the original result. Figure B shows the state-of-the-art result. Our result employing spiral delay lines is illustrated in Figure C. Further, we decrease the height and width of the original routing area and reroute within the minimized routing area. The final routing result is shown in Figure D. For case 6, we calculated the crosstalk magnitude of each wire for each routing result. As shown in the table, our method significantly decreases the maximum and average crosstalk magnitudes. Further, the figure on the left shows that the crosstalk in our routing results is significantly lower than that of other methods for almost every wire. The figure on the right shows that the crosstalk noise level is not notably impacted while the routing area is decreased. In conclusion, our method is reliable in alleviating the accumulated crosstalk noise. That was my presentation, and thank you for your attention.